Hello and welcome to Bedroom Physics. This is the example video for single dimensional motion. I'm going to do two problems. The first problem involves solving for a time, and the second problem involves solving for an acceleration. But first, the one that involves time. So the setup is, we are building a toy rocket, and we are trying to send it up into the atmosphere, but our state regulation only allows us to send a projectile 1,500 meters above ground. The aerodynamics of our rocket is perfect, so let's ignore air resistance. And our rocket thruster allows the rocket to have a net upwards acceleration of 26 meters per second squared. So first, let's make a mental model. And I've drawn this here to help us think about it. So our rocket starts at ground level, and then the thrusters turn on, and it has a constant acceleration of 26 meters per second squared. And then at time alpha, which is what we're looking for, the thrusters turn off. But at this point, since acceleration is constant and velocity is a derivative of acceleration, then velocity is going to be variable. So once our rocket thrusters turn off, our rocket is going to reach a peak velocity. And it's going to continue with that velocity unless another force acts on it. Of course, since we are on Earth, this other force is gravity. So as soon as our rocket, which is giving us a net upward acceleration of 26 meters per second squared, is turned off, then gravity will be acting on it. And it has a downward acceleration of 9.8 meters per second squared. So we've built up an acceleration, but then as soon as the thrusters turn off, gravity will act on it, and it will slow it down. Our goal is to get it so gravity will stop our rocket at exactly 1,500 meters. In order to do that, we need to find the time alpha, which our thruster needs to be turned on to have enough of a peak velocity so it continues up until exactly 1,500 meters. So we're going to think about this problem as a phase 1 and phase 2. Phase 1 is when the acceleration from the rockets are being applied, and phase 2 is when the acceleration from gravity is being applied. That's not to say gravity isn't being applied the whole time. What that means is that the rocket thrusters is giving it an acceleration enough to not only surpass the downward acceleration of gravity, but also give our rocket an upward acceleration of 26 meters per second. So first, let's calculate the distance that it travels just from the acceleration of our thruster. So we're going to use the one that involves time, distance, and velocity. So we have our y1, or y final in the phase 1, is equal to a y initial plus velocity initial times change in time. But remember, since we're starting time at 0, t final minus 0 is just t final. And our t final is alpha, so times time alpha plus 1/2 times the acceleration of the rocket thrusters times change in time, but since we know time initial 0 is just alpha squared. Now, since we're starting on the ground, our y initial is 0. I mean, it can be anything you want, but it just makes it way easier if you have 0 as a reference. Our velocity initial, since it's starting from rest, is 0. And all we're left with is 1/2 times acceleration times alpha squared. So but then we have phase 2, which is when the acceleration is gravity. But we don't have a time for that, right? But we have a formula where we can calculate distance traveled without time. And that's going to be, in this case, our y final is going to be our y max, right? Because there's only 2 phases, and if we can only go to 1,500 meters, then our y final has to be 1,500 meters. So y max is equal to y initial plus velocity final squared minus velocity initial squared over acceleration, but in this case it's gravity, and that's denoted by g for our acceleration, g times 2. So first things first, notice how time is not involved yet. And also notice how we're missing two terms. We don't have y initial and we don't have velocity initial. But wait a second, we do have y initial, right? Y initial is the y final from the first phase, which is y1. It's just the distance traveled from the acceleration of our rocket thrusters. So this is actually just y1. So let's plug that in first and then we'll solve for v initial. And also for v final, we do have it, right? So our final velocity needs to be 0. We want it to stop at 1500 meters. If our velocity is not 0, then it won't stop at 1500. So we need it to be 0. So we have half a alpha squared plus 0 squared, which is our v final, minus v initial squared over 2 times gravity. So remember, this is the y initial for the second phase. Now we have to solve for v initial of the second phase. But v initial of the second phase is the v final for the first phase. And we have a formula to calculate v final. Remember that v final is equal to v initial plus acceleration times time. In this case, the time of phase 1 is alpha. The velocity initial of phase 1 is 0 since we're starting from rest. So is equal to acceleration times time alpha. But our v final in phase 1 is the v initial in phase 2. So this is going to be equal to 1/2 acceleration alpha plus negative acceleration alpha squared over 2g. Now, all that's left to do is some algebra to calculate alpha. So we have half acceleration alpha plus negative acceleration squared alpha squared over 2g is equal to y max. So we want to solve for alpha, and this is actually alpha squared. This is alpha squared. Okay. So since there's alpha squared in both terms, we can take it out. So alpha squared times 1/2 acceleration plus negative acceleration squared over 2g is equal to y max, which means that alpha is equal to the square root of y max over 1/2 acceleration plus negative acceleration squared over 2 gravity root, which is equal to 1500 meters over 1/2 times 26 meters per second squared plus negative 26 meters per second squared times n2 times negative 9.8 meters per second squared, because remember, gravity is an acceleration downwards and our reference acceleration is upwards. So gravity will be negative times negative 9.8 meters per second squared under the root, which is going to be equal to 5.62 seconds. Okay, now on to the second problem. Okay, so for our second scenario, we roll a ball down a hill and it travels for a total of 12 seconds. The first 6 seconds, it travels an unknown distance, and the second 6 seconds, it travels 260 meters. Now, how are we going to approach this? Well, we have t, so we don't want to use the formula that does not involve t. we have a distance, so we don't want to use the formula which doesn't involve a distance. And we need to solve for something that will give us x1. So if we want to solve for something, and we don't want to use the formula without distance, and we don't want to use the formula without time, then we have to be solving for acceleration. So we don't want to use the formula that does not involve acceleration, which leads us to that last and final formula. Now, x final in this case is going to be x2 plus x1, and it's going to be equal to x initial. But x initial is just going to be 0 plus v initial. This starts from rest times time plus 1/2 times the acceleration. Now, the time that it travels in the total distance of x2 plus x1 is 12 seconds. So we're going to have this as, let's just call this time 3, where time 3 is equal to time 1 plus time 2. Okay, and that's going to equal to 1/2 a time 3 squared. Okay, so now we have a formula where we have two unknowns. And if we only have one formula, then we can't solve for two unknowns. We have to get another formula. Well, we might not be able to solve for the magnitude of x1, but we can certainly solve x1 symbolically. x1 is equal to, and since x1 is the first distance, the first 6 seconds, then our x initial and our v initial is going to be the same. Plus 1/2, and it's going to be the same acceleration because this is a uniform ramp, times, now, it's not the total elapsed time, right? This is only the first part. So the first 6 seconds, so we're going to have time 1 squared, which means x1 is equal to 1/2 acceleration t1 squared. So now we can plug this in here, and we're no longer going to have two unknowns, right? Where this formula, the only unknown that's going to be left is acceleration. So if we combine these two, we're going to have x2 plus 1/2 acceleration time 1 squared is equal to 1/2 acceleration time 3 squared. Now all that's left to do is some algebra. We want to get a alone, so we're going to move that over. So x squared is equal to 1/2 a time 3 squared minus 1/2 a time 1 squared, which is going to be equal to a, since they're in both terms, we can take it out, a times 1/2 time 3 squared minus 1/2 time 1 squared. And then in order to solve for a, we're going to divide this entire part by, we're going to divide x2 by this entire part. So x2 over 1/2 time 3 squared minus 1/2 time 1 squared is equal to the acceleration. But remember that we are looking for x1, right? So we're going to plug in this for a here, which is equal to x1. So x1 is equal to 1/2 times, oops, it's not x squared, that's just x2, times x2 over 1/2 time 3 squared minus 1/2 time 1 squared times time 1 squared. And that's going to be equal to roughly 86.7 meters. Alright, this has been the example video for single dimensional motion. Thank you for watching. I'll see you on the next concept video.